As seen with a lot of newer buildings such as ESJ and Clark Hall, there is more of a push for larger amount of windows along the sides of buildings. The issue, though, with an increase in window area is that a lot of energy is lost through glass, mainly due to cooling, lighting, and heating. This project looked to solve the energy crisis by implementing emerging research on transparent wood for window applications and transitioning the lab technology into a market technology. Transparent wood has the intrinsic ability to block ultraviolet radiation, which protects the safety of inhabitants, while transmitting visible and infrared wavelengths to allow for illumination and heating assistance. It also provides greater thermal insulation than standard windows, which could reduce energy usage due to heating, cooling, and lighting. We had a few design goals for our project, the first of which was to fabricate a novel transparent wood window that combines high and low haze wood to try to move from a lab to a marketable technology. We wanted to be better or at least competitive with the current window technology and target market. We also then wanted to determine the ideal grain orientation for balance of desired thermal, optical, and mechanical properties. We then wanted to look at why we combined high and low haze in our window fabrication. There was a compromise between visibility and light scattering with an overall high transmittance. We wanted to minimize the haze in the low haze samples and maximize the haze in the high haze samples. We then, for our last goal, wanted to understand the relationships between size, processing, and properties, and being able to incorporate that knowledge into the design of our window. We based our design calculations for the panes on a 3-point bend loading configuration. Both L wood and R wood were used for our samples since it was important to investigate the property trends of each because grain orientation gives wood anisotropic properties. L wood is cut parallel to the grains, and the grains span the length of the sample. R wood, on the other hand, is cut perpendicular to the grains, and the grains span the height of the sample. In a composite, fracture typically occurs along the interface of the matrix and reinforcement. In R wood, the fracture occurs along the height of the material, creating a clean edge. The L wood has more of a jagged fracture because the crack needs to propagate along the interfaces as it travels across the surface. We looked to compare transmittance and haze properties of glass with low haze and high haze wood at different thicknesses and grain orientations. We focused on how the properties vary over the entire wavelength spectrum, but did most of our comparisons at 500 nanometers since this is the peak wavelength of the sun's emission spectrum. Glass is nearly transparent, and most, if not all of the light is transmitted on axis. Between L wood and R wood, L wood has lower haze, which is why we chose L wood for the window panes so the user can see through it. As the wood epoxy composite gets thicker, less light passes through it, and the light that does get through has a greater proportion scattered off axis. This is due to photons being scattered by the wood epoxy interfaces as well as any defects in the material, both of which increase with thickness. At 500 nanometers, the 0.7 millimeter low haze L wood sample had a transmittance of light of 91% and a haze of 16%, which indicates the amount of light that has been scattered off axis. For another L wood sample that was 6 millimeters thick at high haze, the light transmittance is 62% and the haze is about 95%. The clearwood samples are first measured and cut at the appropriate orientation. The lignin in the samples is removed with a soak in sodium hypochlorite for 24 hours. A solvent exchange then occurs with ethanol and deionized water for 3 hours. The sample is then dried and infiltrated with refractive index matched epoxy. The sample is degassed to remove any air bubbles that may have occurred during fabrication. The first technical drawing depicts the front face of the window. It has both a length and a width of 609.6 millimeters, which is a 2 foot by 2 foot window with a 25.4 millimeter or 1 inch wide frame to mimic existing aesthetics while providing the thermal, mechanical, and haze benefits of the thicker wood. There is no standard window size, but the window footprint was chosen based on the very common 2020 single hung window. The second technical drawing shows the side view of the window. The low haze panes are layered on opposite sides of the high haze frame, which maintains the industry standard 6 mm thermally insulating air gap. The panes are 0.7 millimeters thick, which is the thinnest samples that low haze L wood has been used to make with the current processes. This thickness was checked to ensure that it would withstand high wind speeds and pressure differentials while balancing the aforementioned optical properties of 91% transmittance and 16% haze. The overall transmittance of our proposed transparent wood window is just under 80%, which matches that of double-paned windows currently on the market, while increasing the haziness for uniform illumination over both time and space. Overall, our team found that low haze grain orientation and thickness trends agreed with those of the high haze grain orientation and thickness. The estimated properties of the overall window prototype was based on properties of individual components for comparison with glass windows. The transparent wood technology is young and with limitations, but understanding of its weaknesses will focus the research for improvement. Feasibility will also rely on scalability of processing and sourcing. Our team thanks the following groups and people for helping to make our project a success.